In this set of sample problems, we'll be looking at rotational kinematics. This is the first part of Chapter 11, where we're going back over and looking at the relationships between the angular quantities, angular velocity, angular displacement, angular acceleration. It's similar to the things that we did in Chapters 2 and 4 with linear kinematics. In this first problem, a bicycle wheel rotates uniformly through 2 revolutions. Again, 1 revolution is 2 pi radians, so we need our angular displacements in radians. So 2 revolutions is 4 pi radians. It takes 4 seconds. What is the average angular speed of the wheel? So the definition of average angular speed is the angular displacement, delta theta, divided by the time that it takes. So again, instead of the linear average speed being the displacement divided by the time, that average angular speed is the angular displacement, which is the change in its angular position rather than the change in the linear position x. And so in this, it turned 4 pi radians in 4 seconds. And so this is going to be pi radians per second, or again 3.14 radians per second. Again, just a reminder, radians are unitless, so this could be written just as 3.14 seconds to the negative 1, or 3.14 times 1 over seconds, or 3.14 hertz. Hertz is a unit of frequency. A hertz, 1 hertz is one cycle per second. So again, this is because radians are unitless. And that's important to just know all those different ways of saying that same thing, because sometimes in a question you might be told that the angular speed is 3.14 seconds to the negative 1. And so that might confuse it a little bit. It's just letting you know that that is radians per second if they have it written that way. In this next problem, a bicycle wheel rotates uniformly through 2 revolutions. So again, that's 4 pi radians. In 4 seconds. What's the linear speed of a point 0.1 meter from the center of the wheel? So we have that circle. It has a radius of 0.1 meters. And we're looking for the linear speed, v, of a point on the edge of that circle as this rotates around with an angular speed. Again, we found that the angular speed was pi radians per second from the last problem. And so the relationship between the linear speed and the angular speed is given by the equation that the linear speed v equals r times the angular speed. Again, that came from the fact that arc length s equals r times theta. And so ds dt equals r times d theta dt. But ds dt is the linear velocity. D theta dt is the angular velocity. So the linear velocity here is 0.1 meters times pi radians per second. So again, this is going to give me 0.314 meters per second. Again, so that's the linear speed of a point on the edge of that wheel. If we were looking at a point that was halfway out, it would have half that linear speed. If it was twice as far out, it's going to have twice that linear speed. All of the points on the wheel would have the same angular speed. Again, that's important. As long as it's rotating as a solid object, all the points on that wheel are going to go around, it will go the same number of radians every second. But the points that are farther away from the center are going to have to be moving faster. If you think of a merry-go-round, the horses that are the farther on the outside are going to be traveling with a faster linear speed, but all the horses on the merry-go-round are going to have the same angular speed. It's turning as one solid object, so they all take the same amount of time to go around once, so their period is the same. That means that their angular speed is the same. They're all going to turn the same number of radians every second. It's just farther away. Again, that's going to have a faster linear speed. It's important to know the difference between having the same angular speed and a different linear speed. You should know the difference between them. You should know if the linear speeds are different or if the angular speeds are the same, which ones are going to have a bigger linear speed. That's a very important type of multiple choice question. In fact, you'll see something like that in your homework. In this next problem, we have a cable car at a ski resort that's carrying skiers a distance of 6,800 meters. And the cable which moves the car is driven by a pulley with a diameter of 3 meters. Assuming no slippage, how fast, in radians per second, must the pulley rotate for the cable car to make the trip in 12 minutes? Okay, so first of all, we have this pulley. But the important thing is they tell us the diameter of the pulley. So that means that the diameter is 3 meters, so that means that the radius is 1.5 meters. And we're going to have a pulley on the other side. We're not worried about that pulley. And so we have this belt connecting them, and we have these people, this cable car that's traveling, and it travels a linear distance of 6,800 meters. Now, if there is no slippage, and that's the important statement in this. If there's no slippage, then that means that a point on the edge of this wheel is going to travel the same linear distance as the cable. And that point's going to go around and around and around. And so we're going to look for that point on the edge of that circle to travel a linear distance of 6,800 meters. And we need that to happen in 12 minutes. So one thing that we need is 12 minutes. We need to convert that to seconds. So 12 minutes is 720 seconds. So this cable car is traveling with a certain linear velocity. So the linear velocity of that cable car is the distance, 6,800 meters, divided by the 720 seconds, which is 9.4 meters per second. And if there's no slippage, then that means that the linear velocity of this point on that wheel has the same linear speed. And we have the relationship that the angular speed is the linear speed divided by the radius. So again, that's the similar relationship that we used before. The linear speed equals r times the angular speed. So this is just rearranging it a little bit. So we have 9.4 meters per second divided by 1.5 meters. It's going to give an angular speed of 6.267 radians per second. Okay, now you notice that I drew the other pulley on this other side a little bit smaller. And this isn't asked about, but another common question would be if this is half the radius. They might ask how the angular velocity of that pulley compares with the angular velocity of the other pulley. And the important thing is again, as long as there's no slippage, the linear speed of a point on the edge of this pulley has to be the same as the linear speed at the point on the edge of that pulley. It still has to be 9.4 meters per second. If it's going to have half the radius, then again, the angular velocity is v times divided by the radius. So if it's half the radius, it's going to have twice the angular speed. Again, a smaller pulley is going to have to go around more times to travel the same distance. That's the whole idea with gears on a bicycle. When you're in a lower gear, and there's more to it than that because the idea that we're talking about next, torque, gets into that same idea. But when you're on a smaller gear, you have to turn the pedals more times to turn the wheel a certain number of times. When you're on one of the bigger gears, the pedals don't need to go around as many times for the wheel to turn a certain number of revolutions. Any type of interlocking gears that you have, that's the whole idea of gear ratios, is that one gear goes around a certain number of times and the other one is going to go around less times or more times. It's a way of changing the linear speeds. Again, some of this is done to change the torque that's provided. But for this, if you have that bigger disk, it's going to be rotating with half the angular speed as the smaller disk. So based on this equation, half the radius is going to have twice the angular speed because the linear speed must be the same. If there's no slipping, the linear speeds are the same. It's not the angular speeds that are the same, it's the linear speeds. The linear speed of the cable is the same as the linear speed of the points at the edge of the wheel. That has come up in multiple choice questions. That has come up in some free response questions. So again, that's just something that you need to know. You need to know how those things relate to each other. Okay. In this next problem, a wheel accelerates with a constant angular acceleration of 4.5 radians per second squared. If the initial angular velocity is 1 radian per second, what is the angle that the wheel rotates through in 2 seconds? So what is the angular displacement of the wheel? So this is something we're looking for the angular displacement. I'm going to let the initial angular position be 0. I'm trying to find the final angular position. The initial angular velocity is 1 radian per second. I don't know the final angular velocity. I do know that the angular acceleration is 4.5 radians per second squared. And I know that the time is 2 seconds. So for this, in the problem that we did in the notes already in class, we found this problem where we looked for the angular displacement. In this problem, we're looking for the angular velocity. So to find the angular velocity at 2 seconds, we're going to use the rotational analog of equation 1. So instead of the linear velocity equaling the initial linear velocity plus the linear acceleration times the time, we have the angular velocity equals the initial angular velocity plus the angular acceleration times the time. So the angular velocity is going to equal 1 radian per second plus 4.5 radians per second squared times 2 seconds. So the angular velocity is 10 radians per second. Again, in the problem that we had already done in the notes, we looked for the angular displacement, and so we used equation 2. So we went through and we had found that it had turned 11 radians in that time. So this one was just using the other relationship, going through if you know the initial angular velocity and you know the angular acceleration, you can find the angular velocity at any time. Again, these problems are fairly straightforward as long as you're able to set things up, as long as you can identify what is the initial angular position, what is the final angular position, what's the initial angular velocity, what's the angular acceleration, is the angular acceleration positive or negative, is it speeding up in its angular speed or is it slowing down. All of those types of things are important. You do need to look at those things. That will be something that you'll be seeing in quite a few problems. Okay. In this next problem, how many radians does a 0.3 meter radius automobile tire rotate after starting from rest and accelerating at a constant angular acceleration of 2 radians per second squared over a 5-second interval? So this is asking for the angular displacement. Now, that 0.3 meter radius actually is not going to come up in that first part of the problem. For the second part where it says assume no slipping between the tires and the road, how far did the car move? That's something where you're going to need that radius. So again, sometimes you have to sort through the extra information that you're given. So for this, if I call the initial angular position 0, I'm trying to find the final angular position. The initial angular velocity is 0. It says that it's starting from rest. The angular acceleration is 2 radians per second squared. And the time is 5 seconds. So again, for this, we're going to use the rotational equation 2. It's going to be the angular position equals the initial angular position plus the initial angular velocity times the time plus 1/2 times the angular acceleration times the time squared. So this is 0 plus 0 times 5 plus 1/2 times 2 radians per second squared times 5 squared, which is going to be 25 radians. Again, whether it's a 0.3 meter radius automobile tire or it's a 50 meter radius Ferris wheel, it doesn't matter. It's going to rotate through the same number of radians if it starts from rest and it has that angular acceleration. The thing that the radius of the tire affects is the linear distance that the car moves. And so the linear distance, s, equals r times theta. And so if there's no slipping between the tires and the road, then this point on the edge of the wheel, it's going to travel through some specific linear distance, s. In fact, that's just, this is definitely not to scale. 25 radians is going around, 3.5 to 4 times. So this is going to go around several times, and there's going to be this point of contact along the road. And so it's going to travel this certain distance, s, along the road. And that distance that travels along the road is going to be the length of the edge of that circle. So that linear distance is going to be 0.3 meters times 25 radians. So it travels a linear distance of 7.5 meters. Again, you just need to be careful if the question is asking for the angular position, the angular displacement, or if it's asking about the linear distance that it travels. Again, there's a relationship between them. You'll have to go through that relationship. You'll have to understand how to do that relationship. But these are important types of problems. A wheel starts from rest and rotates with a constant angular acceleration to an angular speed of 12 radians per second in a time of 3 seconds. Find the angular acceleration of the wheel, and then find the angle in radians through which it rotates in this time. So for part A, again, the angular acceleration is the change in angular velocity divided by the change in time. Again, that doesn't say anything different than equation 1 does. It's just rearranging it. I think this is a little bit easier way of writing it. So we're going to have 12 radians per second minus 0 radians per second divided by 3 seconds. So that gives an angular acceleration of 4 radians per second squared. And then to find the angle that it rotates through in this time, since we know the time and now we know the angular acceleration, we can use equation 2. So the angular position equals the initial angular position plus the initial angular velocity times the time plus 1/2 times the angular acceleration times the time squared. And so we have 0 plus 0 times 3 plus 1/2 times 4 times 3 squared. So this is going to be 18 radians. So if you remember back in chapter 2, it was very common to have to use something to try and figure out the acceleration, and then to use that acceleration to solve for other parts of the problem. So this is the same type of problem. A car goes from rest to 10 meters per second in 5 seconds. What's the acceleration of the car? Then how far does the car travel in 15 seconds? It's the same type of problem. Again, it's just dealing with rotations, so you have to understand how to translate it into the rotational situation. Okay. In this problem, a car accelerates uniformly from rest and reaches a speed of 22 meters per second in 9 seconds. So again, that 22 meters per second, that's the linear speed of the car. That's something that's extremely important. If you look at that, again, just from the units, it says that it's in meters per second. So meters per second, that's an absolute, positively huge clue that this is a linear speed. Angular speed is radians per second. So pay attention to the units. It's very easy to get linear speed and angular speed confused. So this car accelerates uniformly from rest and reaches a speed, so it doesn't say an angular speed, it reaches a linear speed of 22 meters per second. The diameter of a tire is 0.58 meters. Through how many radians has it rotated during this time? Okay, so the first thing to do is you somehow have to convert that linear speed to rotational quantities. And another important thing is this is giving you the diameter of the tire. So the radius of the tire is half of that. It's going to be 0.29 meters. And so if you're going through and doing this, you can either convert that linear speed to the angular speed and calculate the angular acceleration that way. Or I can go through and I can use this linear speed to calculate the linear acceleration of the car, and then from that I can find the angular acceleration, because that linear acceleration of the car is the tangential acceleration of the wheel, and there's a relationship between the tangential acceleration of the wheel and the angular acceleration. So I'm going to go through and I'm going to find the linear acceleration of the car. So again, I'm looking at the linear quantities. So the linear acceleration A is the change in velocity over the change in time. So it's 22 meters per second divided by 9 seconds. So that's 2.444 meters per second squared. And then from this, we can calculate the angular acceleration. So the angular acceleration equals the linear acceleration divided by the radius. And again, this is the tangential component of the acceleration. And that linear acceleration of the car, that is how quickly the edge of the wheel is speeding up. And so this is going to be 2.444 meters per second squared divided by 0.29 meters. This is going to give an angular acceleration of 8.429 radians per second squared. Okay, now that we have that, I can go through and answer the questions. So part A, through how many radians has it rotated during this time? So if I'm using equation 2, I know that this final angular position equals the initial angular position of 0. This is starting from rest, so the initial angular velocity is 0, plus 1/2 times 8.429 radians per second squared times 9 squared. And that's going to give an angular displacement of 341.375 radians. Again, similarly to what I had done on the last problem, I could have gone through and I could have found the linear distance traveled from kinematics, and then using the arc length, that linear distance equals r times theta, I could go through then and calculate this angular position that way. They both would be just as correct. One's going through and converting to the rotational quantities first. One's going through and converting to them at the end. Doesn't matter which way you do it. Whichever is easiest for you to see, that's what I recommend that you do. Okay. For B, how many revolutions did it make? Again, that's something to pay attention to. On some of the homework questions, they're going to ask you to answer in terms of revolutions, or they'll give you something in the problem in terms of revolutions. So in part B, you divide your angular displacement by 2 pi. So 1 revolution is 2 pi radians. So 341.375 radians times 1 revolution over 2 pi radians. So again, I'm just dividing by 2 pi, and I get 54.331 revolutions. Again, one revolution is 2 pi radians, so one revolution is 6.28 radians. So it's a little over 6. So 341 divided by 6 is going to be a little over 50. So 341 divided by something a little bit bigger than 6 is a little bit bigger than 50. And then what is the final angular speed in radians per second? The angular speed equals the initial angular speed plus the angular acceleration times the time. So it's going to be 0 plus the angular acceleration of 8.429 radians per second squared times a time of 9 seconds. So this gives an angular velocity of 75.861 radians per second. So again, think about a car that's speeding up. As it goes faster and faster, its wheel rotates faster and faster and faster. And so this is the angular speed of that wheel at the end of that acceleration. So it's been speeding up that entire time. So it's going around pretty quickly. A tub in a washing machine goes into its spin cycle, starting from rest and reaching an angular speed of 15 radians per second in 8 seconds. At this point, the person doing the laundry opens the lid and a safety switch turns off the washer. The tub slows to a rest in 12 seconds. Assume a constant angular acceleration as the tub is starting and stopping. Through how many radians has the tub rotated during this time, and then how many revolutions did it make? Okay, so going from A to B is going to be pretty easy. You're just going to take your radians and divide it by 2 pi. But to answer part A, this problem has several parts to it. It has 2 parts to it. It has the speeding up, and it has the slowing down part. So we did these types of problems when we had linear kinematics, where we had to go through and we had to break it up into pieces. So the first thing that I need to do is I need to figure out the angular acceleration of it speeding up. The angular acceleration is going to equal the final angular velocity minus the initial angular velocity divided by the time. So I'm going to call this my first angular acceleration, because this is for the first piece. So it goes from rest to 15 radians per second. So this is 15 radians per second minus 0 radians per second divided by 8 seconds. So this gives my angular acceleration for the first piece as 15 divided by 8. So it's 1.875 radians per second squared. Okay. For the slowing down piece, the angular acceleration over that second piece is the final angular velocity, so it stops, 0, minus the initial angular velocity of 15 radians per second. And this takes 12 seconds. So the question is a little bit unclear. Does it reach a stop in a time, at t equals 12 seconds when t equaled 8 seconds at the beginning part? The way that this is worded, it looks to me as if it's saying that the tub is slowing to rest in an additional 12 seconds. This isn't going to slow down and stop immediately. I mean, that would strip some gears. So this is going to be the 15 radians per second divided by 12 seconds. Otherwise, if it says that at t equals 8 seconds, it reaches a speed of 15 radians per second, and then at t equals 12 seconds, it has gone ahead and it has stopped. Then when I would calculate this at this spot right here, instead of using 12 seconds, I would use 12 minus 8, so I would use the fact that it took a time interval of 4 seconds. But again, that's not what we have happening in this problem. So 15 divided by 12 is 1.25, but this angular acceleration is negative. So we get negative 1.25 radians per second squared. Okay. So during the speeding up time, I need to figure out how far it has turned. And then during the slowing down time, I need to figure out how far it turns additionally. So for part 1, the initial angular position is going to be 0. It's starting from rest times 8 seconds plus 1/2 times my angular acceleration of 1.875 times 8 seconds squared. So this gives me my angular position at the end of the first part as 60 radians. Okay. Now for part 2, it's already moving at 15 radians per second, and it has already turned 60 radians. So my angular position at the end is going to be my initial angular position, which is 60 radians, plus my initial angular velocity, which is 15 radians per second, times an additional 12 seconds, plus 1/2 times negative 1.25 radians per second squared, times 12 squared. So this is going to give me a total angular displacement. You know, there's nothing else that I have to do. This takes it all into account. So I have 60 plus 15 times 12 plus 0.5 times negative 1.25 times 12 squared. So again, that negative term is taking off some. So this gives me an angular position of 150 radians. And so that's the full angle that it has rotated through during the 8 seconds for the first part and then the 12 seconds for the second part. It rotated 60 radians during part 1. It rotated an additional 90 radians during part 2 for a total rotation of 150 radians. Again, the important thing is in part 2, even though it was slowing down, it was never rotating the opposite direction. It kept spinning the same direction. It kept spinning in the positive angular direction, which would have been the counterclockwise direction. So again, this is the answer to part A. And then for B, 150 radians times 1 revolution over 2 pi radians gives me 23.87 revolutions. So this washing machine drum turned 23.9 times while it was speeding up and then slowing back down. Okay, and then the final one I want to look at is something that's similar to that. So we have a grinding wheel initially at rest that's rotated for 8 seconds with a constant angular acceleration of 5 radians per second squared. And then the wheel is brought to rest with a uniform negative angular acceleration in 10 revolutions. So first I have to convert that to radians. So 10 revolutions times 2 pi radians in 1 revolution gives an angular displacement of 62.8318 radians. And so determine the angular acceleration needed. So that 10 revolutions is after it's starting to slow down and stop. So to do this, you first need to go through and find the angular speed after the 8 seconds. So we get that from equation 1, that the angular velocity is going to equal the initial angular velocity plus the angular acceleration times the time. So it's starting from rest. It's 5 radians per second squared times 8 seconds, which is 40 radians per second. So this is rotating at 40 radians per second, and then it's going to slow down and stop in 62.83 radians. So we're going to go through and we're going to use equation 3. So it's stopping. The initial angular velocity is 40 radians per second. Again, we're only looking at this piece where it's slowing down. And 2 times the angular acceleration times the angular displacement of 62.832 radians. So if you solve this, you have 40 squared divided by the quantity 2 times 62.832, and that angular acceleration is negative. So we have an angular acceleration of negative 12.732 radians per second squared. And then how long did it take to bring it to rest? So again, this time is measured after the 8 seconds. We're not including anything about that 8 seconds. That was only used to figure out what the angular speed was before this switch was thrown and it starts to slow down. So now that we know the initial angular velocity and the final angular velocity, and we know the angular acceleration, we could just use equation 1. So we have 0 equals 40 plus negative 12.732 times t. So that gives a time of 3.1416 seconds. Again, for our answer, we end up getting pi seconds. The way it's worked out with the revolutions, you could go through and you could figure that out. We do get pi seconds for this to slow down and stop. Again, these problems are very similar to things that you have already done, that you've already seen. You really just need to get practice with them. You have quite a few problems on the homework. There's about 15 or so of these that are these angular velocity, angular acceleration, rotational kinematics type problems. But again, they come up in a lot of other things where you're going to be using that for some of the pieces of it. Again, I will be doing this for all of the things that we have here in Chapter 11. I'll be doing a lot of extra sample problems. I strongly encourage you to go through and look at these sample problems. It's going to make the homework much simpler.